Hello everyone, and welcome to MechLearn 360. All right, so in this video I want to teach you deflection of beams. We are looking at simply supported beam with uniform distributed load, or sometimes called UDL for short. All right, so if you have something like this, how are you going to find the deflection of this beam? That's what we are interested in right now. All right, so without wasting much time, let's get started. Now, the first thing that you are going to do is to find the reactions at the support. Okay, so let's try and find the reaction at the support. Now, one thing that you also have to know is that whenever you have a distributed load is a load which covers a certain part of an area. Okay, so to be able to find the equivalent load, this is what you are going to do. So you are going to assume that if I take each portion, there is this load. Okay, therefore the average load on the entire section which I will get is going to be like a form of a rectangle. All right, so this load is occupying the form of a rectangle. And what's the area under the rectangle? That is the length by the breadth. So we are going to assume that the length is the L that we have here, and the breadth is the load, which is P that is coming. So it's going to be P multiplied by L. Okay, and that P multiplied by L will act at a certain portion, which is actually nothing but the center. So let's assume that the center is here. So we are assuming that the center is here. So what we are trying to say is that the load will have one. We want to represent this whole section portion by a certain one load. Okay, and we are calling it PL, and it's going to act at the center. That's all what we are trying to say. So this distance is L/2, and again the distance here will be what L/2. Okay, so right now we know that this is PL and this is L/2. This is also L/2. Let's try and find the reaction forces. Let's call the reaction force here RA, and let's call the reaction force which is here, let's call that one RB, right? Okay, so how can we find the reactions? Equilibrium of forces or equilibrium of rigid bodies. So summation of forces should be 0. Every force moving up rather, because there is no force along the X. So if you look at this, then we are going to get RA, which is going up, minus PL, which is coming down, and then plus RB should be equal to 0. Right now we are done with this part. We can say that RA plus RB should be equal to PL. Okay, let's call this equation 1, and then we are going to sum moment about, let's say, point B. Clockwise is positive, should be 0. So we are summing moment about this point B. So what is the moment of RA? It's going to be clockwise. RA will be clockwise. Okay, so RA multiplied by the length, and the length, so L. Then we come to this force, which is PL, and the distance is half of the distance, so it's going to be my L/2. But then look at it carefully. You can see that the PL is coming all this way here. So the moment that is going to cause about point B is going to cause it in the counterclockwise direction. So it's going to be minus PL, which is the load. Then we multiply it by what? L/2, which is the distance. Then we equate it to 0. Okay, because we cannot take RB, because that's the moment, and that's the B is the point, so we cannot take the moment of B. All right, that's all. So right now, what can we say? We can say that RA multiplied by L should be equal to PL multiplied by L/2. But then the L here will cancel the L here, so we can say that RA is going to be PL divided by 2. And then since we know RA now, we can go back to the equation and solve for RB. So RB is going to be PL minus RA, which is nothing but PL minus what? PL over 2. So essentially, if we have PL and then we have PL over 2, then that is like half. So it's going to be 1 minus half, which is the same as PL over 2. So essentially, what we are trying to say is that the reaction at A is PL over 2, and then the reaction at B is also what? PL over 2. Very good. So right now that we have the reaction, then it means we can go ahead and then we can look at our deflection. So let's look at our deflections together. All right. So to be able to solve for the deflection, we would actually take a portion. So instead of looking at the whole beam at a point in time, you look at just a portion of the beam. Okay, just a portion. So just take a portion of the beam. Now, if we take just a portion of the beam and try to draw it, we will get so we are going to get something like this. We are going to just take that small portion of the beam and bring it down. So it's going to be something like this. And then the load that we have here is what? PL over 2. That is the reaction. But don't forget that there is this UDL here. Okay, don't forget that there is this UDL which is happening here. All right, because even if you take it, look at it carefully. If you take a portion here, it is still there. Okay, it is still there. So now this is what we are going to do. Once you have taken a portion here, and then let's call the distance from here all the way here. Let's call that distance. Okay, let me bring it down. Let's call this whole distance from here to here. Let's call it X. Okay, let's call it X. And then right now, since we have this load, so the distribution here will, let's call it P with respect to what? X. In other words, okay, let me do it this way. This is what we are trying to say. You know, the load that was here, that was P. Let me do it this way. The load that was here, that was P, which was distributed. Since we have brought the load here, the P is still distributed here. And then it is distributed about a distance of what? X. So what do you think will happen? When we were dealing with this one, we said that we will multiply the area, we will multiply the actual length of the beam, the whole of this length, by what? P. And that is what we did here. But now we have taken a portion. So since we have taken a portion, that will be X and this will be P. So what do you think will happen? The load that is going to act on this small portion is like PX. Okay, so simply put, this is a uniform distributed load of P, and then it is acting on a small portion called X. So the magnitude of that load will be the area, which is what? PX. All right, and that PX will act exactly at half X. I hope the concept is clear. So please, it's going to act here. Let's call that PX, but then the distance is going to be what? X over 2. So meaning that here is also okay, let me bring it to the middle small. So it's going to be something like this. Yeah, so the load will come in like this, and then this one will come here. So this distance is what we are calling X divided by 2. Okay, so X divided by 2. All right, once you're able to get this distance correct, then that is it, because we are now going to start. Okay, all right, so so you've seen something like this here. What this means is that there will be a shear force coming down here. Let's call it V, and then there will be a moment coming this way. Let's call it MX. Now, basically, we are doing this because we have taken a section. So that is why the moment and the shear force is coming there. We call it internal forces. All right. So now that we have been able to do this, let me try and magnify this small. All right. Okay. So now that we have been able to do this, then we will have to come up with the equation. Okay. So let's sum forces. Okay, let's sum forces. Summation of forces. Summation of forces. Every force going up should be positive, should be 0. Then we can say that PL over 2 is equal to minus V is 0. In other words, PL over 2 minus PX and then what? Minus V should be what? 0. All right. And then in other words, what is V? So V, which is the shear force, will be PL over 2 minus PS. That's all. So the shear force will be PL over 2 minus what? PX. And interestingly, this is what the shear force is telling us. But you know, there is something that we call moment and shear force. Now, interestingly, if I have moment and I integrate moment with respect to x, I get, if I integrate shear force with respect to moment, I get moment. Sorry, please, let me go over it again. If you integrate shear force with respect to distance, you will get moment. Okay, let's try to integrate this and see what will happen. But I will do something again and you confirm it. So let's integrate this with respect to s. Is going to be PL over 2, then x will come here. And then minus, if I integrate px, is going to be p multiplied by x squared divided by 2. So you see this here. Okay, put it somewhere. Put it somewhere. Now let's come here. Let's come to what we have here. And then you know what we are going to do? We are going to sum moment about where we have taken the cut, this point, this portion. We are going to sum moment about where we've taken the cut here. Now if we sort of try to take moment, let's do that. Let's call that moment. So summation of moments about x should be 0. Clockwise is positive, okay, for equilibrium. Already we have this mx which is going that direction, so counterclockwise. So small mx, that one is going there. Are we okay? Then what else? We have px. So what is the moment of px about s of x over 2? That distance is going to be px multiplied by x over 2. But I see that the px is coming in the anti-clockwise direction. So it's going to be px multiplied by x over 2. So it's going to be minus px multiplied by x over 2. All right. And then what else? Then we have what do we have again? We have this one, PL over 2. We have PL over 2. So the PL over 2 is also going to go in the, as for that one, it will be in the clockwise direction. So it's going to be PL over 2. All right. So plus PL over 2. And what is the moment distance? It's x. Okay, that is x. All right. So so that is it. So we've got this equated to 0. Now, if I ask you to make mx the subject, what do you think will happen? If you make mx the subject, all right, so you see that the mx, I think there was a mistake here. Mx is going anti-clockwise. Okay, so that mx was supposed to be negated, this one. All right, So let's make that ms the subject. Simply put, if I make that mx the subject, there is going to be pl over 2x minus px squared over 2. Oh, what do you see here? You see that this one is the same as what we just did. So at this point, what I can tell you is that when you get something like this, you can either integrate the shear force to get the moment, or you can sum moment to get the moment. I hope you are okay. So the choice is yours. All right. So at this juncture, once you've been able to do this, then it means you are almost there, because we would have to just, bring the mx here and do the integration. That's all. All right. So now, let's bring it here and do the integration. So it's going to be ei d squared y dx squared should be equal to what? PL over 2x minus px squared over 2. So you've got this, and then you want to do the integration. What is it going to be? So it's going to be pretty much simple. We would have to integrate this. Now, please take notice, if you have d squared y and you integrate, it's going to be dy dx. All right. And then you want to integrate. Please take the constants aside, and then integrate x. You're going to get x squared over 2 minus p over 2. Put it one side, then you get x cubed. So you are integrating x squared. So it's going to be x cubed over 3. Is that right? Plus a constant c1. Always, whenever you do integration, you bring a constant. All right. So now at this point, we know that ei is dy dx should be equal to what? PL x squared divided by 4 minus px cubed divided by 6 plus c1. So how can I find c1? Boundary condition. So I need boundary condition. I'll go back to the equation this side here. Then I'll go back to the diagram. Then I'll ask myself, what is happening? So now this is actually a simply supported beam. So we expect that the deflection will be of this form. Okay. So the deflection is going to be of this form. Is that right? Which is going to come in that sense. But then we expect that the maximum of all of the deflection will be where? At the center. Okay. But then, okay, this is what they are saying. If I have a curve like this, at the turning point, the slope will be 0. That's all. The y dx is 0 at the turning point, which is what? At x equals L over 2. So let's bring that idea here and say that at x equals L over 2, the y ds is 0. All right. So from here, we can go forward and say that ei dy ds, which is now 0, should be what? PL over 4, 0, minus p over 6, 0, and then plus what? C1. All right. So at this juncture, it means that the C1 that we are actually interested in is 0. Okay. C1 is 0. Okay. So right now that we know that C1 is 0, let's move forward and write it again. So we know that C1 is 0. So, but you cannot assume that C1 is 0, so you will not calculate it. If you don't calculate it, how would you know that it is 0? Okay. So P over 6 x cubed, that's all. So this is what we call your slope equation. All right. So this is your slope equation. All right. At this moment, you have gotten your slope equation. So now let's try and find okay, I'm coming. All right. So yes. Okay. So this is the slope equation anyways. Now let's come up with the expression for the deflection. Okay. All right, so now that we have gotten the boundary condition at x equals L over 2, dy dx is 0, let's go back to the equation and put it inside. So we have ei y dy dx is 0, pl over 4 x squared. Now x is L over 2 squared minus p over 6 x cube, which is what? L over 2 cube plus what? C1. All right. So right now we need to solve for C1, isn't it? So 0 is equal to PL cube divided by what? So 4 multiplied by 2 times 2, which is basically the same as saying that 4 multiplied by 2 squared. All right. This is 16 minus what? PL cube, and then 6. So 6 multiplied by 2 cubed. All right. So that gives us 48. All right, plus what? C1. So from here, what can we say? So we can say that C1 will be PL cube over 48 minus PL cube over 16. But because they are the same, let's factorize PL cube out. 1 over 48 minus 1 over 16. So that our C1 is going to be 1 divided by 48 minus 1 divided by what? 16. And what is that? Minus 24. Minus 1 over 24. So it's going to be PL cube divided by 24. Okay, so that is the value of C1. This this C1 here inside this one. Okay. So it's going to be what? So the slope is ei dy dx, and then we are going to put inside so PL over 4 x squared, PL over 4 x squared minus px cubed over 6. So minus px cubed divided by 6, and then plus C1. So now that we know the C1 is PL cube over what? 24. All right, so we've got this. Yeah, okay, so we've got this as our deflection equation. Sorry, this slope equation. So this is our slope equation. All right. Now that we have gotten our slope equation, let's try and find the maximum slope. Where would the maximum slope occur? What do you think? Okay. So now if you look at it carefully, the slope is coming from this way like this, and then it is coming to 0 like this. It means that the maximum slope might have occurred at x equals 0. So simply put, the maximum slope is occurring at x equals 0. That's all. So if I want the maximum slope, I will say that at x equals 0, dy dx is what? Is equal to maximum. Maximum. Therefore, I can just go ahead and say that ei dy dx maximum will be what? 0. I'll put 0 here. I'll put 0 here. So the final answer is going to be minus PL cube over 24. Meaning that the formula for finding the maximum slope is given by minus PL cube over 24 ei. That's all. Where P is the load. Okay. All right, so so we've got the maximum slope. Let's do the deflection and then the maximum deflection. So we will go back here into the slope equation and then integrate so that we will get the the deflection equation. Now if I integrate the slope, I will get the deflection, which is going to be PL over 4. Then let's integrate x squared. That is going to be x cubed divided by 3 minus. Then I'll do P out of 6. Then I'll integrate x cubed is going to be what? X cubed, this one is going to be x4 divided by 4 minus P. So you treat this constant because there's no x. And you just bring x here. That's all. Plus what? A constant C, C2. All right. So at this juncture, okay, let's write it together. So it's going to be PL over 12 x4 C2. So how can I find C? So you realize that at x equals 0, at x equals 0, the deflection was 0, y is 0. In fact, we can even say that at x equals L, y is also 0. But then the simplest way to go is to say that x equals 0, y is 0, so that we can go faster. Now, if we do that, then we can say that wherever we have x, we should put 0 there, y will also be 0. If we do that, interestingly, 0 will be 0 minus 0 minus 4. So we can go ahead and say that our 4 cube, x4, and then minus PL cube over 24x plus C2. Once we've been able to get this, C2 is 0. Now let's go ahead. This is the deflection equation right now. That's what we are trying to say. So deflection equation. Now let's find the maximum deflection at the midpoint or center. So for a simply supported beam where the slope is 0, this is where the deflection is maximum, and that is where the center at x equals L over 2. So we will go ahead and say that at s equals L over 2, our y is what? Y max. Once we're able to do this, then we can go ahead and say that, okay, so y equals y max. So we can just say that EI y max is what? PL over 12, and then we will put x cubed, which is what? L over 2 cubed, and then minus what? P over what? 24 x4, which is L over 2 to the power 4, minus what? PL cubed over 24 x, which is what? L over 2. And then from here, what do we have again? EI y max will be what? Okay, so PL4 divided by what? So 12 okay, so what are we getting? All right, so we will get 12 multiplied by 2 cube, 96. Then minus PL to the power 4. Then, so 24 times 2 raised to the power 4. And that is 384. Minus PL4. And then the last one is going to be 24 multiplied by 2. 48, right? Okay, so let's simplify everything. Let's simplify everything here. So we have PL over 4. So let's factorize it out. PL over 4 is common. So we have 1 over 96 minus 1 over 384 minus 1 over 48. Let's punch this on our calculator and then let's see what we will get. So it's going to be so 1 divided by 96 minus 1 divided by 384 and then minus 1 divided by 48. And what is that? Minus 5 over 384. So it's going to be minus 5 PL4 over 384, meaning that the maximum deflection. So it means that the maximum deflection, which is Y max, is actually going to be minus 5 over 384 EI. And then here will be PL4. So 5. So in fact, this formula here is the formula for the maximum deflection. All right. For a simply supported beam which is having a uniformly distributed load. Okay, so thank you very much for watching.